Hello students, welcome to the class on Principles and Chemical Applications of Thermodynamics, and we are now covering the basic aspects of thermodynamics before we proceed to chemical applications. And in today's class, I am going to focus on this very important topic, work, a part of which we have already discussed, but I will carry forward our previous discussion on work and talk about what I mean by the importance of work in the first law of thermodynamics. Now, we have already seen that if I consider the pressure volume work done by or on an ideal gas, then this is the generic definition of what work done is in a finite process, as it takes the system from an initial state 1 to a final state 2. And here, please remember that dV is the change in volume of the system as the system undergoes this change in state, and P external is the external pressure against which the system is changing its volume. Now, if my working system is an ideal gas, only then I can use this second relationship, which is pressure into volume of the gas, that is equal to number of moles of the gas, N, the universal gas constant, R, and the temperature of the gas, T. And you already know that this is the ideal gas equation, which expresses the essential parameters of the system in terms of each other. Now, when I talk about the work done by isothermal expansion of an ideal gas, so if it is a reversible isothermal change, we have already seen that at every stage of this reversible change, where I take an infinitely large number of steps in going from the initial to the final state, P external must be equal to P at every stage of the process. And therefore, I can write down this expression where I have replaced the external pressure by the pressure of the gas. And once again, let me emphasize that this is valid if and only if the transition from state 1 to state 2 is being carried out by a reversible process. Now, since I have an ideal gas, I can replace the P here by the corresponding expression expressing P in terms of its temperature and volume and the number of moles. Now you see, look at the integrand, and you see that the integrand is now a function of temperature and volume and N. So if I have a closed system, N is constant. If I have an isothermal process, then T is also constant. So I can take nRT out of this integration and carry out the integration of dV over V. And the result that you already know is minus nRT ln V2 by V1. Now, obviously, this expression tells me that if I have this PV indicator diagram, then the area enclosed by these 4 points and this entire big area is equal to the amount of work done in this reversible process. Now, if I think about an irreversible isothermal change where work is being done by against a constant pressure where P external is equal to Pf. So, you understand now that this irreversible work done, that will have this P external still here, and I can take it out of the integration simply because the work is being done against this constant pressure. And in that case, I can put Pf, which is this value, the final pressure of the gas, and evaluate the amount of work done as this. So what does this correspond to? This corresponds to the area of this rectangle as shown in this figure. So from these two figures, we can immediately conclude that maximum work is done by the system when it is undergoing a reversible expansion, under which condition the magnitude of work done is always greater in the reversible process in comparison to the irreversible process. And I arrive at this conclusion by a visual expansion of the two areas. One, this hatched area, another is this entire big area under the curve, where this portion is nothing but how pressure is varying at every stage when the volume is infinitesimally adjusted in the process of reversible isothermal change. Now, when we have understood this, then the next task is to go and try and understand how much work is done when we are talking about an adiabatic expansion of the ideal gas. So first law of thermodynamics tell me that for an infinitesimal adiabatic expansion, dq is equal to 0. And therefore, if I put it back in this in the infinitesimal representation of the first law of thermodynamics, dq would be equal to 0, and I must be having dw is equal to du. Now, since it is an ideal gas and I know that u is a function of temperature and temperature only, and therefore I can write down du as NCV dt. Therefore, I now have a handle of estimating the amount of work done in a process like this by looking at this equality, that dw equal to NCV dt. Therefore, if I integrate on both sides, what I get is the work done in a process where the system passes from an initial state 1 to a final state 2, that will be given by NCV T2 minus T1, where this expression I have obtained by integrating this side. Now, what does it tell me? It tells me that I can estimate the amount of work done provided I know the specific heat of the system, number of moles present, then the final temperature and the initial temperature. So this is a very specific method by which we can find out the work done in any adiabatic expansion of an ideal gas. Now let us have a look at how to do this estimation and find out the final temperature T2 in a reversible adiabatic expansion. Now, in the case of a reversible adiabatic expansion, you know from your high school days that all these three expressions, that PV to the power of gamma equal to constant, T into V to the power of gamma equal to a constant, or this relationship, all these three are valid. So depending on the information available to you, you can find out the final temperature T2. And then you can put it back in this expression and find out the magnitude of W. But similar considerations do not apply when you are dealing with an irreversible adiabatic expansion. Okay, so when you are carrying out an irreversible adiabatic expansion, you are doing so against a constant external pressure, and let us say that under such condition P external is equal to P2, that is the constant final pressure of the gas. So in that case, there is a different prescription for obtaining the final temperature. You would understand that the work done under such condition is given by minus P external into V2 minus V1. And since it is an adiabatic expansion, I can still say that W or delta U under such condition is equal to W. Now I replace delta U by its expression like NCV T2 minus T1, and I equate it to the amount of work done that in this irreversible adiabatic expansion against this constant external pressure. So that expression must be minus P external into V2 minus V1. Now I will play around a little bit. What I will do is I will replace P external by P2, and I will replace V2 in terms of the final temperature T2 and the final pressure P2, and I will replace V1 in terms of the initial temperature T1 and the final initial pressure P1. So now what do I have? I have NCV T2 minus T1 equal to minus P2 into this term within the bracket. Now I will rearrange it and write the final temperature as T1 into this quantity in the numerator and this quantity in the denominator. Now what's the use of doing this? The idea was to find out the final temperature that the system will achieve when it is made to undergo an irreversible adiabatic expansion against a constant pressure. And here you find that quantity precisely. Now what does it depend on? Look at the right hand side. You should be knowing the initial temperature, you should be knowing the initial pressure and the final pressure and some measurable quantity of the system, that is CV. And therefore, if I know which state P1, T1 that the system is starting from and the temperature where it is starting from, and if I know which pressure it goes to, which is the constant external pressure, in that case I can find out T2. And once I can find out T2, what is W? W is nothing but NCV T2 minus T1, as I have mentioned above. And therefore, I would say that if you know the initial and the final states of the gas, or you know enough information about the way the system is undergoing a change in state, it is possible to find out the work done for either the isothermal or the adiabatic expansion or compression of the gas as it passes from the initial equilibrium state to a final equilibrium state. The next topic that I would like to highlight over here is the fact that work is path dependent. For this purpose, I have chosen to work with a closed system containing some ideal gas. And in this case, as shown in this particular PV indicator diagram, this green line shows a PV isotherm. So it is at a given temperature T. Now I am going to start from this initial equilibrium state where the system has an initial pressure of 10 Pascal and an initial volume of 1 meter cube at a given temperature T. And I am going to look at the change in state such that the final equilibrium state is given by a pressure value of 1 Pascal and a volume of 10 meter cube. Therefore, when I am looking at the change in state, this is my initial equilibrium state and this is my final equilibrium state. Now I am going to devise the first path as a reversible isothermal expansion. And therefore, what I mean by this is that as I go from this initial state to this final state, my system will traverse along this isotherm as shown by the green curve. And my question is, can I find out the amount of work done as the system evolves from this initial state to the final state along the green curve? The answer is as follows. I understand that here nRT must be equal to PI/VI, where PI is the initial pressure and VI is the initial volume of the gas, and this must also be equal to the final pressure of the gas multiplied by the final volume of the gas. So where did I get this relationship from? I got it from the ideal gas equation. Now I can very easily use the results that I have obtained in the first part of my lecture and write down that the work done can be now evaluated using this expression. But do I have all the informations that I require to evaluate these quantities? I understand that I haven't given you the value of N or T, but obviously I can use this expression and write down W as minus PI/VI into ln of Vf/Vi. Now, from the given conditions, do I know all the quantities that are present on the right-hand side of this equation? The answer is yes. I know that Pi is 10 Pascal. I also know that Vi is 1 meter cube. And then I also know what V final is, that is, V initial is 1 meter cube and V final is 10 meter cube. So if I put all of these things together, this is how I am going to find out the magnitude of the work done in this process. And if you calculate, you find out very easily that work now is given by minus 23.02 joules. And you understand that I'm using here the unit conversion that 1 joule is equivalent to 1 Pascal meter cube. So along path 1, as I go from this initial equilibrium state to this final equilibrium state, the work done is minus 23.02 joules, and I would emphasize on this minus sign in front of the numerical value simply because this is work being done by the system. Now let me go ahead and think about the same pair of initial and the final equilibrium states, but now I take another path to go from this initial state to the final state. And now I have devised a two-step expansion, and these are shown as follows. I start from this initial state where the pressure of the gas is 10 Pascal and the volume is 1 meter cube. And then I do an isochoric compression, and therefore I come from this point to this point, whereby the pressure of the gas remains constant, decreases, and it decreases to 1 Pascal. And its volume remains constant, and that's the reason why I call it an isochoric compression. Now, when I do this isochoric compression, you understand that there is no change in volume. And since the work done that I'm talking about is always dependent on the change in volume, therefore, in this case, I must be having work done is W1 equal to 0. Now, in the second step, what I do is I go from this initial step to this final step, and this is nothing but expansion of the gas from a volume 1 meter cube to a larger volume 10 meter cube against this constant external pressure P2 equal to 1 Pascal. Okay, so in this case, what is the amount of work done? In the second step, then work done must be minus P2 into V2 minus V1. So I put back all the quantities that I know for this experiment. I know what P2 is, that is 1 Pascal. I know what V2 is, that is 10 meter cube. and I know what V1 is, that is 1 meter cube. And therefore, I find that in this along this second path, the amount of work done by the system is minus 9 joule. Now, I will move forward and find out the total work done as I pass from this initial state to this final equilibrium state. So for that purpose, I will add up W1 and W2, and the answer is then minus 9 joules. Now there is a third experiment that I am going to do now, whereby I will take a third path between the same pair of initial equilibrium state and the final equilibrium state. But now my first step is an expansion against a constant external pressure of equal to P1 of 10 Pascal. So this is what is shown here. So this is the initial step, and then I have carried out an expansion from a initial volume of 1 meter cube to 10 meter cube against this constant external pressure of 10 Pascal. So this is 10 Pascal. Now in this case, I use a second step, which is this isochoric compression, where the pressure becomes 1 Pascal. So as before, I can find out what is the amount of work done in the first step. That would be minus P1 into V2 minus V1. Why P1? Because the expansion is carried out against a constant external pressure of P1 equal to 10 Pascal. And therefore, I can evaluate W1 to be minus 90 joules. And the second step is an isochoric compression. So following the same logic as before, we can say that W2 is equal to 0. If that is so, then what is the total work done? So I add up W1 and W2, and that turns out to be minus 90 joules. So as you see here, we have started from the same set of initial equilibrium state, ended up in the same final equilibrium state, but by following 3 different paths. The first one was a reversible isothermal expansion, and the next two were two-step irreversible expansions, but they were different. Now, if you look at the magnitudes of work done, you find that the work done in each case have different magnitudes. All of them are negative because the system is performing some work on the surrounding, but as you see that the maximum work has been done in this particular case, and this is actually quite clear by the fact that this particular system has the maximum area under the initial and under the condition shown here. Now we can give you a practice problem where I say that certain amount of xenon is contained in a container at 2 atmosphere and 298 Kelvin. I am asking you to calculate the work done if the gas undergoes expansion under various conditions. So it may be isothermal reversible expansion, or it may be isothermal irreversible expansion against a constant external pressure, or the same two experiments could have been carried out by maintaining adiabatic conditions. So here, while solving this problem, I understand that my initial equilibrium state is characterized by P1 equal to 2 atmosphere and T1 is equal to 298 Kelvin. And I also find that in a closed system, I am using roughly about 0.5 moles of the ideal gas. So when I am looking at isothermal reversible expansion, therefore, the expression that I require is minus nRT ln P1 by P2, where I have replaced V2 by V1 by the corresponding values of P1 and P2, and this is the expression. And T is the temperature that remains constant, and therefore here T is equal to T1. Therefore, on the right hand side, I know all the quantities. I know P2 because the final equilibrium state is characterized by P2 equal to 1 atmosphere. I know P1 and T, and therefore I can find out the value of W. If I carried out the same isothermal expansion under irreversible condition, in that case I would say that my W is minus P2 into V2 minus V1. Okay. Now here P external is P2, that is equal to 1 atmosphere. Now what is V2? V2 I can very easily find from ANR T1 by P2. And what is V2? And what is V1? So this is V2 and this is V1. And then what you find is, you can also find what V1 is. And once you know V2 and V1, and since you know what P2 is by your experimental condition, you can find out W. Now let us have a look at the adiabatic expansion. Now when I am doing the adiabatic expansion, I can either do it by a reversible way or I can do it in an irreversible way. What would be the difference? If I start from the same initial equilibrium state, I see that if I follow a reversible path, I would arrive at this temperature. But if I follow an irreversible path, then I would arrive at a very different temperature. But if I know the final temperatures of the final equilibrium states, I can very easily go ahead and calculate the work done in this process, as is shown by the expressions here, which I have already discussed. Now I will highlight the values of work done in this slide here. But before you calculate, I would like to remind you of the fact that I have started from the initial equilibrium state defined by these parameters. I know that my P2 is 1 atmosphere. Therefore, when I am having a reversible adiabatic expansion, in this case, which expression shall I use to find out the final temperature? Obviously, since I know the initial temperature, initial pressure and the final pressure, I would be writing it as T1 to the power of gamma, P1 to the power of 1 minus gamma, and I am going to equate it to T2 to the power of gamma into P2 to the power of 1 minus gamma. And from this equation, I am going to find out what the value of T2 is. On the other hand, when I have this irreversible adiabatic expansion against this constant external pressure, P external equal to P2, knowing P1, P2 and T1, I can find out T2. So that is exactly what I have been talking about in the previous slide to be necessary for estimating the amount of work done. I would also like to highlight over here that the work done during a compression and work done during an expansion are very different, and they become equal in magnitude only when the experiment is being carried out between the same pair of initial and the final equilibrium states by doing a reversible expansion. So, if you have infinite intermediate stages, it is only under that condition that the expansion work is equal to the compression work. So, finally, we have seen the different processes with which we can actually compute the work of expansion. We can also compute the work of compression. And this we are going to use later on when we evaluate the practical applications of thermodynamics in many chemical applications. Thank you.